Okay, so at this point, we've talked about the partial pressure of oxygen and carbon dioxide and how that helps move the oxygen and carbon dioxide around to where it needs to go. We talked about how oxygen is carried by hemoglobin in the blood, and now we're going to talk about carbon dioxide in the blood. Okay, so how does it get around inside the blood? So in the blood, in the blood, a tiny little bit is going to be dissolved into the water, into the plasma, but not very much of it can do that. A tiny little bit is going to be held on to the hemoglobin, so the hemoglobin can actually hold on to carbon dioxide as well. But the vast majority of about 70% of it is going to be converted into a different molecule, which is called bicarbonate, and then carried around in the plasma in the form of bicarbonate. And that's going to have a secondary function of acting as part of a buffer system to help neutralize or help keep the blood a particular pH range. And we'll talk about pH of the blood in a couple of weeks. So let's talk about how that works. So here we have carbon dioxide. Remember that carbon dioxide is produced from cellular respiration, which means that the concentration, the partial pressure of carbon dioxide is going to be very high in the tissues because they're constantly making more carbon dioxide. And so that means that the carbon dioxide that is produced by the cells of the body are then going to diffuse along their partial pressure gradient from high pressure to lower pressure into the blood. Once it's in the blood, a small little bit of it will be dissolved in the blood. But again, we don't want too much of that to dissolve in the blood because if you increase the amount of carbon dioxide, more of it will combine with water, and that creates a molecule that's called carbonic acid. And acid, what does an acid do? Acids release hydrogen. That's what an acid is, a molecule that releases hydrogen. And so that's going to increase the concentration of hydrogen ions, that decreases the pH, and we don't want that. We do not want our plasma to become too acidic, because that is going to damage our cells and denature our proteins, and that's bad. Okay, so we need another way to do this equation to get to the bicarbonate. And the answer to that is that reaction, so this reaction here is instead of occurring in the plasma, it's going to be contained and it's going to be contained inside of the red blood cells. Okay, so here's how this works. So that carbon dioxide is then going to enter into the red blood cells. Here are our red blood cells. Now, inside of the red blood cells, we're going to use an enzyme, which is called carbonic anhydrase, ASE, that makes it an enzyme. It's going to help combine the carbon dioxide with the oxygen, and it'll do the same equation as we saw before, but now we're inside. That creates the carbonic acid, H2CO3, that's carbonic acid. See how it has extra hydrogens to give off? And so it will give off the extra hydrogens, and then we have, so we do have the extra hydrogens giving off, but we are inside of a cell, so we don't have to worry about acidifying the entire blood because we're inside of the red blood cells, and the red blood cells can neutralize this in other ways, usually by taking that hydrogen and combining it to proteins, because proteins are negative, sometimes even the hemoglobin itself. So the hemoglobin can sequester or help neutralize that extra hydrogen so that the whole blood will not become acidic. Then we have the bicarbonate left over, and the bicarbonate is going to then leave the red blood cell and go back and travel in the plasma. So the bicarbonate ion, which is this HCO3 minus, it's a minus here because it lost a plus. It has an extra electron because it took the electron of the hydrogen. Okay, so the bicarbonate ion is going to leave the red blood cell and travel around in the plasma. But you need to make sure that you're balancing the positive and the negative charges here. So if you're going to have a negative ion leaving the cell, you need to add a negative ion. So if you lose a negative ion, you need to add a negative ion so that you don't end up reducing the charge inside of the cell. So what you do is when you lose that negative bicarbonate ion, you're going to take the chlorine back up. That's called the chloride shift. You're shifting the chloride into the cells to offset the loss of the bicarbonate. That's the chloride shift. Okay, then that bicarbonate is just going to travel around in the plasma to wherever it needs to go. It eventually will find its way to the lungs. Now, in the lungs, remember, because you have atmospheric air in there, the partial pressure of the carbon dioxide in the alveoli is going to be lower than the partial pressure of the carbon dioxide in the blood. That's going to make it so that the concentration of carbon dioxide is going to go down as the carbon dioxide is leaving towards the alveoli. Okay, so think of this equation a little bit like a seesaw, right? If it goes down on one side, it's going to drag the whole equation in that direction, right? So when you decrease the carbon dioxide over here, that drives the equation in the opposite direction. Okay, so here's how it works. The bicarbonate ion that is found just in the plasma, again, we use it as a buffer when it's not being used for this. The bicarbonate ion will then re-enter into the red blood cells, and the red blood cells are going to take that bicarbonate ion, combine it to the bicarbonate. Sorry, take that bicarbonate ion, combine it with the hydrogen ion, so just take it away from the hemoglobin and put it back on the bicarbonate. You then recreate the carbonic acid. Then you'll use the same enzyme that you had before, carbonic anhydrase, to then split that carbonic acid back up into carbon dioxide and water. The water is nice and neutral, it just hangs out in the cell. The carbon dioxide, because of the partial pressure differences, will be drawn out of the cell and then out of the blood and into the alveoli so that you can breathe it out. Okay, so you're just doing the opposite of what you did before. Okay, so again, if you're going to gain a negative, you need to lose a negative. Now you have these extra chlorides in there, so you can lose some of those. That's called the reverse chloride shift. The chloride shift, remember, was when you were taking the bicarbonate away from the cell. Now you're bringing it back into the cell and you're losing the chloride. That's the reverse chloride shift. It combines with the hydrogen, creates the carbonic acid that's then split into carbon dioxide and water. The carbon dioxide then travels along its partial pressure gradient from high to low into the lungs. Breathe it out from there. Okay, so most of the carbon dioxide is transported as bicarbonate ion, about 70%. The chloride shift is caused by, okay, so it has to do with the bicarbonate ions leaving. If you lose a negative, you have to gain a negative. And so the chloride is going to come into the cells to balance that change in charge. So what would D be called? D is called the reverse chloride shift, because the chloride will then leave again as you take on the bicarbonate to go back the other direction. So I have a couple of videos here. I suggest that you go into the PowerPoint slides and then you can click on the videos to watch them. Okay, that's enough for this piece. We're going to go into ventilation next.